Swayam Prabha. Digital India. Educated India.
Welcome back to this online class on diffusion in multi-component solids. Today, we are going to solve diffusion equation for multi-component system. So, we will consider the infinite diffusion coupled boundary conditions and we will consider a multi-component system containing n components. When it comes to multi-component systems, there are n minus 1 independent concentration variables. And so, when we define the flux of one component, we need to consider the concentration gradients of all the n minus 1 independent components. So, based on Onsager's formalism of Fick's law, we can write the equation for a flux in an n component system as for a component I. The flux of component I is j I tilde is equal to minus summation of j equal to 1 to n minus 1 d I j tilde n dou C j by dou x. So, the flux of component I is related to the gradient of component j through the interdiffusion coefficient d I j tilde n. The superscript n here denotes that component n is taken as the dependent component. Now, there are n minus 1 independent concentration gradients, that is why j varies from 1 to n minus 1. So, to define the flux of one component, we need n minus 1 interdiffusion coefficients, and we have n minus 1 independent fluxes, because if we assume the molar volume to be constant, then the summation of all j I tildes I going from 1 to n is equal to 0. So, the nth flux is dependent. So, we have n minus 1 square interdiffusion coefficients that define the interdiffusion completely in an n component system at a particular composition. Now, we are going to assume that this set of interdiffusion coefficients is independent of composition for solving this equation. Let us see how do we solve the diffusion equation for an n component system. So, if we consider as an example a quaternary system, which means there are 4 components. So, 3 components are independent. So, we can write 3 interdiffusion fluxes. So, the flux for 1 j 1 tilde is given by minus d 1 1 tilde 4 dou C 1 by dou x minus d 1 2 tilde 4 dou C 2 by dou x minus d 1 3 tilde 4 dou C 3 by dou x. Similarly, flux of component 2 j 2 tilde equal to minus d 2 1 tilde 4 dou C 1 by dou x minus d 2 2 tilde 4 dou C 2 by dou x minus d 2 3 tilde 4 dou C 3 by dou x, and the third independent flux j 3 tilde is given as minus d 3 1 tilde 4 dou C 1 by dou x minus d 3 2 tilde 4 dou C 2 by dou x minus d 3 3 tilde 4 dou C 3 by dou x. To get to the diffusion equation, we can apply the continuity equation for individual components. So, we can write dou Ci by dou t equal to negative dou Gi tilde by dou x. So, if we expand this continuity equation again for the 3 components, we can write dou C1 by dou t is equal to, since we are assuming that all the dij tildes are constant, we can take them outside and we can write the right side as d 11 tilde 4 dou 2 C1 by dou x2 plus d 12 tilde 4 dou 2 C2 by dou x2 plus d 13 tilde 4 dou 2 C3 by dou x2. Component 2 dou C2 by dou t equal to dou d 21 tilde 4 dou 2 C1 by dou x2 plus d 22 tilde 4 dou 2 C2 by dou x2 plus d 23 tilde 4 dou 2 C3 by dou x2, and for the third component dou C3 by dou t equal to d 31 tilde 4 dou 2 C1 by dou x2 plus d 32 tilde 4 dou 2 C2 by dou x2 plus d 33 tilde 4 dou 2 C3 by dou x2. So, we can see in multi-component system the diffusion equation is coupled, which means if we consider the partial of any one component with respect to time, it is expressed in terms of second derivative or the second partial of each of the independent component with respect to x. And so, we have a problem here how to solve this coupled equation. So, we first need to decouple the equation, and we can do that easily if we use matrix algebra, right. So, if we carefully look at the equation for the fluxes, for example, here it is easy to see that we can express this in the form of a matrix equation, right. If we define a column matrix of fluxes on the left side, column matrix of gradients on the right side, and a square matrix of interdiffusion coefficients, right. So, we can write the Fick's law equation as J tilde n in general is equal to minus d tilde times dou by dou x of C. So, in this case, if we write this for a quaternary system, we can define these matrices as J tilde is a column matrix of 3 independent fluxes, which are J1 tilde, J2 tilde and J3 tilde. C is a column matrix of 3 independent concentrations, C1, C2, C3, and D tilde is a square matrix. In case of quaternary, it is a 3 by 3 matrix containing the 9 interdiffusion coefficients, which are D11 tilde 4, D12 tilde 4, D13 tilde 4, D21 tilde 4, D22 tilde 4, D23 tilde 4, D31 tilde, D32 tilde and D33 tilde. We can also write this diffusion equation in the form of a matrix equation, right. So, if we write this 3 diffusion equations in the form of matrix, we can write dou by dou t of C is equal to d tilde times the second partial of C. Okay. So, how do we proceed now? This is a matrix equation. Now, to make it even simpler, let us try to transform the original matrices into a new form. Let us call this new form as a cap basis, right. So, what we do? We have to first define what we call as similarity transformation matrix for D tilde. So, this similarity transformation matrix P is defined such that if we pre-multiply D tilde by inverse of P and post multiply D tilde by P, we get a diagonal matrix delta. Right. So, here delta is a diagonal matrix and it is obtained by arranging the eigen values of this D tilde matrix along the diagonal, right. So, delta is D1, D2, D3, right, and these DIs are eigenvalues of D tilde, and matrix P is obtained by arranging the eigenvectors of D tilde column by column. And for convenience, we write this matrix such that the diagonal elements are normalized to 1, right. So, the eigenvectors are written such that the corresponding diagonal elements are normalized to 1. So, P can be written as 1, beta 1, gamma 1, alpha 2, 1, gamma 2, alpha 3, beta 3, 1. Now, to proceed further, what we do? We define fluxes and compositions in a new basis, which we call as cap basis. So, we obtained the matrix J cap by pre-multiplying the original matrix with P inverse. So, J cap is equal to P inverse times J tilde, and C cap is obtained by pre-multiplying the original matrix C with P inverse. So, how this transformation helps us? Let us try to look at it. So, if we now pre-multiply this diffusion equation in the matrix form with P inverse, we get P inverse times dou by dou t C is equal to P inverse times D tilde dou 2 by dou x2 of C. Now, we are assuming that D tilde matrix is constant, and so this P inverse or P, this all these matrices are also constant, and so we can take them inside the derivatives, right. And we know P inverse times C is nothing but the matrix C cap, right, the new cap basis. So, we can write dou C cap by dou t is equal to, on the right hand side we do a little trick here. We insert a matrix which is defined by the product of P and P inverse. What is P times P inverse? It is an identity matrix. So, if we insert P times P inverse between d tilde and dou 2 by dou x 2 term, the first term will be P inverse d tilde times P, which we know is delta, and the term P times P inverse was here. So, P inverse remains, we can take this inside, and P inverse times C is again the matrix of concentration in cap basis C cap. So, we can write this as dou 2 C cap by dou x 2, right. So, we now by the transformation got the diffusion equation in a simpler form. In terms of individual components of this, right, you know, C cap would be a column vector of C 1 cap, C 2 cap and C 3 cap, and delta is a diagonal matrix. So, individually we can write dou C I cap by dou t is equal to d I times dou 2 C I cap by dou x 2. So, we have now obtained a decoupled partial differential equation, right. So, which looks now easier to solve, right. But we also need to look at the initial and boundary conditions now, right. So, the way we defined the initial and boundary conditions. So, initial condition for, remember, for a diffusion couple, it is a step function, right. So, if I draw the diffusion couple boundary condition again here. So, if we consider any single component, on the left terminal alloy composition was C I minus, and on the right terminal alloy the composition was C I plus to start with, and it is a step function. So, at x equal to 0 there is a discontinuity, and the thicknesses of the two blocks are such that the diffusing species does not penetrate all the way to the other end. So, these ends are minus and plus infinity. So, the concentration of the alloy block remain as the original concentration in the two ends, that is at plus and minus infinity. So, initial condition is C I at any x at time t equal to 0 is C I minus, right, when x is less than 0, and it is C I plus when x is greater than 0. What is the boundary condition? C I at minus infinity at any time t should be the original concentration, that is C I minus, and C I at plus infinity at any time t should be C I plus. And when we solve the diffusion equation for the binary diffusion couple, we also used the condition C I at x equal to 0 at any time t would be, since the diffusivities are constant, this should be average of the two end concentrations, right. This should be C I minus plus C I plus divided by 2. Now, if we define this in terms of matrices, we can write C is equal to C minus, where C is the matrix of concentrations, C minus is the matrix of 3 independent concentrations in the left terminal alloys, right. This is for x less than 0, and should be equal to C plus for x greater than 0. C plus is the column matrix of 3 independent concentrations of the right terminal L1. Similarly, we can write the boundary conditions C at minus infinity t is equal to C minus, C at plus infinity t is equal to C plus, and C at 0 t we can write as 1/2 C minus plus C plus. We can apply the similar transformation to the initial and boundary conditions. So, if we pre-multiply on both sides by P inverse, we get the concentrations in cap basis, right. So, if we pre-multiply both sides by P inverse, then we can write C cap is equal to C cap minus for x less than 0 would be equal to C cap plus for x greater than 0, C cap at minus infinity t would be C cap minus, C cap at plus infinity t would be C cap plus, and C cap at 0 t would be half C cap minus plus C cap plus, right. So, we have to solve now this diffusion equation, and the initial and boundary conditions are defined by this matrix equation. So, if we write in terms of individual components CI's or CI caps, then we will see that now we have obtained a decoupled partial differential equation with the initial and boundary conditions, which we have solved before for binary diffusion, right. Except that here the concentration variable is now defined in the new basis, the cap basis, and instead of the single diffusivity term that appeared earlier for binary diffusion, here what we see is d I, the small d I, which is the eigenvalue of d tilde. Now, we know the solution for this, right. So, we have derived the solution for this. So, if we write the solution for C I cap, we will see C I cap is equal to C I plus cap plus 1/2 into C I minus cap minus C I plus cap into 1 minus error function x over 2 root small d I t, right. Remember, we are using the eigenvalue of d tilde instead of the single diffusivity term t. For binary, there was a single diffusivity term here, right. So, we obtained the solution for concentrations of I in the cap basis, right. We can rearrange the term and write this solution as 1/2 C I cap plus 1/2 C I cap minus 1/2 error function x over 2 root d I t times C I cap minus C I cap plus. Now, if we want to get back to the original basis, because we want the solution for composition in the original basis, right. So, we first need to convert this into matrix form. So, if we write this in the matrix form, we get C cap is equal to half C cap plus half C cap minus half ERF. So, ERF is a function that I will define. So, times C cap minus minus C cap plus, and this ERF is nothing but the matrix, it is a diagonal matrix defined by arranging the error function terms. You see the error functions are appearing in the solution for C I cap. These error function terms for different components are arranged along the diagonal of this matrix. So, ERF matrix is defined as, it is a diagonal matrix. So, error function of x over 2 root d1 t 0 0 0 error function of x over 2 root d2 t 0 0 error function of x over 2 root d3 t. Now, to get back to the original basis, what we need to do? We defined the cap basis as P inverse times C equal to C cap. So, if we pre-multiply now by P, we get back the original matrix, right. So, if we pre-multiply by P on both sides of this equation, P times C cap is the matrix C, right, should be equal to P times C cap plus is C plus the matrix of independent concentrations of right terminal alloy. So, half C plus plus half P times C cap minus is C minus the matrix of independent concentrations, more specifically column matrix of independent concentrations of left terminal alloy, minus half times P times ERF. Now, again we smartly insert P inverse times P, which is an identity matrix between ERF and this bracket. So, what we will get? P inverse times P, and if we pre-multiply that P with C cap minus and C cap plus, we get back the C minus and C plus matrices times C minus minus C plus, right. So, this is the solution for all the concentrations in a multi-component diffusion couple. Okay. We can arrange this in a better, more good looking form as C is equal to half into I minus P times ERF times P inverse times C minus plus half into I plus P times ERF times P inverse into C plus. This is a very simple looking solution in the matrix form. And remember, I illustrated this for quaternary while deriving the solution, but this is applicable for an n component system. Okay. Just to verify, if I apply this for binary system, right, for binary we have a single diffusivity term, right. So, d is same as di, there is only one di and it is same as the diffusivity term. Also P is equal to 1 and we get back the solution that we have derived, right. C is equal to C plus by 2 plus C minus by 2 minus 1/2 error function x over 2 root dt times c minus minus c plus, and if we rearrange the term we get the more popular form c minus c plus over c minus minus c plus is equal to 1 half 1 minus error function x over 2 root dt. Remember this matrix ERF here for binary will have only one term, right, that is error function x over 2 root dt, where d is the binary diffusivity there. So, this can be verified for binary. Okay. So, the advantage of using the matrix approach for solving the diffusion equation with the transformations that we did is very clear here, right, because we could solve very simplistically and got a very simple form of solution. Now, people have derived before the solutions for ternary, and you can see it can take a very complicated form, right. So, the advantage of matrix approach is we get the solution in a very simple form, right. For example, if you want to see the solution for a ternary system which was derived earlier by Fujita and Gosting. So, this is the solution for ternary concentrations, right. We have two independent concentrations C1 and C2, and you can see it is a very complicated form, but using the matrix approach we obtained the solution in a very simple form. Okay. So, we will stop here for today. Thank you.